Welcome to the AbsInt Videocast for the April release 24. My name is Christian Humbert and I'm going to present the latest features and improvements in the binary level analyzers of AbsInt, namely StackAnalyzer, aiT worst case execution time analyzer, TimeWeaver, TimingProfiler, and the ValueAnalyzer add-on. As usual, I'd like to start with presenting the improvements and changes in the graphical user interface, followed by the latest features for selected binary level analyzers, like in this case the interactive value analysis, StackAnalyzer, TimeWeaver, and last but not least some improvements or changes in the aiT specification language. Let's get started with the first feature in the graphic user interface, which is more an optical than a functional improvement. We now support the Windows non-default color schemes, and especially also the Windows dark mode with the aiCube. So if you change the color scheme, for instance, to dark, the analyzer GUI will look after a restart like this. The next change concerns the interactive value analysis. In this example, I had started the analysis with this interactive play button here and opened the graph already. Now, when I close the graph view, in the previous releases, this also closed the value analysis process in the background. Now, starting from this release, when I close the interactive graph, you can see in the home that we are still running the analysis in interactive mode. So this icon indicates it. And in order, if we want to reopen the graph again, we can do that, and we can even still access, for instance, the value analysis result. You see, it's still present, the process in the background. But when I want to close that process, you have to do it explicitly. You have to go here and do a right mouse click on the analysis item and click on Close Interactive Analysis. And then you see the background process will be terminated. For the demo of the next point on the list, I'd like to first create a new stack analysis item. For instance, the 10 millisecond task. I copy the name here to the ID field, and let's group it under stack usage analysis. Makes sense. Now I have two analysis items for two different tasks. In the last release, I showed already how to edit multiple analysis items at once by selecting them, multi-select them, and click on Edit Analysis. Here you can modify some properties, some common properties. For instance, also introducing a name-specific report file. So you can see that now we have here task 1 millisecond task context file and a 10 millisecond task text report file here specified at once. But this time I'd like to show how to clone multiple analysis items at once. This is all possible, for instance, also from the overview here. So you can multi-select the items again and click via the context menu to clone analysis as. Now you can decide to which analysis type you want to clone this to task analysis, for instance, to WCAT analysis with aiT. As you can see, by clicking on clone, two new analysis items are automatically generated based on the previous stack usage items. Of course, it would make sense to regroup them in an aiT group, right? Next point in the list concerns the message handling and the message view especially. For that, let's go back to the 1 millisecond task stack usage analysis. I have here under the control flow and stack analysis an info message. It's just a green one, not an error, not a warning, but just an info message that tells us that while resolving a certain annotation, computed call, which was resolved by a user annotation, while resolving it, we are reading some 8 bytes from, well, a writable section. And this message is special since it has exactly 2 file references, namely a reference to the annotation file where we specified this annotation, and also to the original C code file. So if you go here, right mouse click, you see that in show in file you have 2 references. But starting with this release, we now also introduce explicit 2 line location references here, so that you can also directly go here and say, I'd like to go there, show in file, and you are immediately in the annotation file, while if you click that one and say show in file, you end up immediately in the original source file. So it's a bit clearer and better distinguished. The next one is we have a revised double-click behavior to messages, in especially if, for instance, no corresponding view is already opened. So for instance, in this case, if I would like to open or show a message in the graph by double-clicking to it, you see now a new automatically opened context menu. When I did a double-click, that will automatically be opened, and it will ask a user now where I would like to show the message-related program point, so in the call graph, in the disassembly, or again in our 2 files, and then the user can select which one to go. If the graph, however, is opened already, going back to the result, to the warning, double-clicking again will assume that you would like to visualize the program point in the already opened view, in this case the graph. The next new feature is the new table of contents for the report file. For that, I'm going to the report file we have generated here. And if I open that, you see now a new table of content here on the left side of the report file. So let me make it a bit bigger, with selected sections. So you can, for instance, immediately jump to the resulting maximum stack usage, which lists the worst case path, or to the value analysis statistics. So this is a selected set of interesting sections of the report file. The last point on the list is a convenience feature when formulating result combinations. So let's do that. Let's create a result combination here for computing the overall stack usage for a certain stack area, for instance, stack area 1. And our formula shall look like this. We assume that task 1 millisecond and task 10 millisecond are operating on the same stack area and can preempt each other. So that means we would basically have to summarize or to add the stack usage results of both tasks plus some offset for the context change. You know that there is a possibility to refer to an analysis group. So you could do, for instance, sum add, and then take the name of the group. I have it already in the paste buffer, and add some, for instance, offset, and then it will basically take the results from the 1 millisecond and 10 millisecond task, sums it up, and adds the 64, which ends up with 416 bytes. But sometimes you want to explicitly refer to individual analysis items, not to entire groups, and for that you had to always go here and copy the name of the ID and then say, okay, hash, here, hash, and then the name plus go back to the next one, copy this one, Go here, say hash that one plus 64. Now you can also use the context menu in the result combinator. It offers the so-called insert result and does it for you. So you can say, I'd like to take the 1 millisecond task can1 sum and add it to the 10 millisecond task result and add the offset. This is much more convenient and easier to use, I think. All right, this concludes the presentation of the new features of the graphical user interface. Let's continue with the analysis-specific changes. The next feature I'm going to present affects customers only who have licensed the ValueAnalyzer add-on. You might have seen this new option here for non-value analysis items. It's called Enable ValueAnalyzer Features. It affects the license token allocation, the ValueAnalyzer token allocation for non-ValueAnalyzer items. So if you would like to use so-called static ValueAnalyzers assertions in non-ValueAnalyzer items, you now have to explicitly enable that option. Otherwise, the assertion will not be taken into account. So to demonstrate that, I'd like to show you, we have here in this analysis a variable called felt. And this variable is accessed here. It's written only on the worst case path. And we could now go ahead and, for instance, formulate a static assertion, which is of course incorrect. We could say that the variable is expected to never be written in this task. Okay, let's do that. So if I go to the ICE file and say here area felt, it's the name of my variable, and I say assert writable false. Save that annotation and rerun the analysis without ticking that option. You see what happens. The analyzer complains that it will ignore the ValueAnalyzer annotations since the ValueAnalyzer features are not enabled for this analysis. Of course, if you do an interactive analysis, which will allow you to interactively explore the ValueAnalyzer results, that will always allocate ValueAnalyzer token. But for the standard non-interactive mode, but also checking the static assertions, you now have to tick that option. If you do that and redo the analysis, we see the effect. Now the analyzer takes the assertion into account and says, well, the ValueAnalyzer detected definite assertion failures. Please consider the report file for more information. Well, let's do that. Let's go to the report file quickly, the local one. Here we have a new section. It's called Memory Accesses, Watched Areas, and Access Assertions. We can click here in the table of content to it, and we see, okay, our area, this is the memory area for the felt array, was observed as an assertion, and we have here some assertion failures. Reported that in this context the protected area was written. Okay. Here's definitely written, and here's written perhaps if we have some unsharp, imprecise write accesses in the value analysis. All right. Let's stay for a moment in the interactive value analysis exploration to show you the next feature. For that, I'm going to start the interactive analysis again. As you know, the value analyzer, which is working internally for basically all our binary level analyzers or analysis types, is a very powerful static analysis. It comes with several domains, not just an interval based domain. We also have some relative domains, some explicit stack related domain. And when you go to a program point and say show value analysis results like this, or using the shortcut V, then the analyzer gives you an overview about the data flow values that are present at the selected program point. For the different domains here, the register domain, the memory cell domain, also the register relational domain, or the, as I said, the stack domain, for instance, the stack relation domain. And now you could say, I'm just interested in seeing the memory cells. So you could go here, filter. Now this is a new feature, the domain filter. You could say memory cells. And then we just see the domain for the memory cell data flow values. Okay, and this shows that the analyzer has collected an information that this memory cell contains the following content. For instance, if you want to see the stack relative domain, we could filter for stack, and then we see that, and this is induced by the instruction. The instruction moves the content of the register x29 to the stack pointer, and this is exactly what we see here. The analyzer collects the information that the content of x29 is now put to the stack as relative to the stack pointer on a certain, and this is the offset from the stack pointer, initial stack pointer value. So this helps to better concentrate on domains you're really interested in. The next feature is StackAnalyzer specific. We have introduced with release 24 a new consistency check between what the analyzer has computed as a worst case stack usage for a task and the size of the allocated stack area which the user has specified. For that, I have prepared a short example. First, I have defined a stack area label since in my binary here I don't have a symbol for a defined stack area. And usually in customer specific applications I've seen that individual stack areas are labeled by the application with some symbols. To overcome this here, I just introduce my own stack area label. But if you have a defined label in your symbol table or in your section table of your binary, you can of course directly use that symbol. So in this example, I have defined a stack area 1, which is going from this address here to EFF. So basically 256 bytes of allocated stack. Yeah. Now I go to my setup hardware view, and as you know, here you can provide a stack pointer, initial stack pointer address, and also a stack area. For this example, I'd like to first provide the stack area, which is basically my stack area 1, so the range, the full address range of the stack area 1. And since the stack usually grows downwards, I'd like to start with my initial stack pointer at the end of the stack area 1. So we could formulate this stack area 1 end address, but as we have seen in the defined stack area, this ends up with a non-aligned or 4-byte non-aligned address. There are some architectres which require an aligned stack pointer. So what you could do is we could omit a few bytes and say we would like to start with a 4-byte aligned end address, and it will automatically select the correct address. So we can see, we can check that. So if we run the analysis now, and unfold the control flow in StackAnalyzer, we see we have an annotated user stack pointer, which is now the aligned stack address to FC instead of FF. And we have an annotated stack area, which corresponds to the address range of our defined label, right? Okay, so now what happens if I reduce that stack area? So for instance, basically we have seen that this that we need 224 bytes of worst case stack usage for this task. Obviously enough stack space allocated, but what happens if this stack usage either grows or the stack allocated stack area is reduced, for instance, by some 31 bytes, for instance. and no, this should no longer be sufficient. If I now run the analysis, you see the following. This was already present in previous release versions. The register as P is loaded with an incompatible value. So we have we had a consistency check already for the case that the stack pointer register content is always precisely known over the entire analysis. So, or in other words, the data flow value for the stack pointer at any program point will never get lost. Then the analyzer will automatically find a contradiction as soon as we are leaving the address range defined under the stack area range here. But what happens if that absolute stack pointer content gets unknown for some abstraction reasons? We of course still have the relative stack pointer modifications analysis. So I'd like to simulate what happens if it gets unknown. You don't have to really understand what I'm doing here. I'm just simulating that the stack pointer content get absolutely unknown. And in the previous versions, we no longer had this contradiction since the analyzer did not know anything about the concrete SP address content anymore. And so it could also not restrict those addresses with the range and come to a contradiction. But in this new version, we always do a consistency check. Also for the case that the stack pointer value has become unprecise or even completely unknown. You now get a new error message that tells you that you have more stack space used, namely 224, than available in the configured stack area. So the stack area we have simulated the shrink to just 221 bytes, and so we are exceeding that stack area, which is obviously a potential stack overflow problem here. So we have more consistency check here. The next point on our release features list is the TimeWeaver related improvements. We are now introducing two new features for our hybrid worst case execution time analyzer, the so-called trace-based mode analysis feature, and we also have extended our trace coverage statistics now to also show per context coverage. All right, to give you a demo on these two features, I have prepared a small benchmark program here. Currently you see the source code, the original source code of that benchmark program. And the main and interesting part of the entry function is that one here. We have a sequence of if statements where we check the value of an external main task clock. So, and especially we check if the task clock tick here is unequal, is odd, and then we would enter executing this sequence. If it is every fourth tick, we would execute this one, and so on. Yeah. So as you can see, just from a logical point of view, only certain combinations would make sense here to execute these sequences. So for instance, that one could go together with that task clock here, but certainly not the first two ones together, right? Because this one is definitely even, and this one is definitely odd, the main task clock. So the analysis does not know anything about the task clock as it comes from outside. Maybe in a sensor or an external clock. And when we analyze this now with TimeWeaver, and even if we have several runs of that entry main function, all of these runs, I think we have 29 in our examples, will be put together. And then in the very last step, the path analysis searches for the absolute longest path. And it might happen because if we do not have any information about main task clock, then that the analysis selects, like we see that here in some example graph, selects as a worst case a highly overestimated setting scenario that we enter here this if then else branch the sequence, but we also enter in the worst case this sequence for the modulo 4 equals 0 case. and for the modulo 10 equals 5 case as well, and so on. So basically highly overestimated. And well, in the last release, we have shown you how to distinguish these modes using the value analysis. So you could introduce so-called value analysis modes here in the project. You could analyze it assuming that your main task clock modulo 2 equals 1. You could analyze a separate analyze if it's modulo 4 equals 0, and so on. Or basically you can list all the different values for the main task log you want to distinguish. And then the analyzer just excludes those combinations which cannot happen in the physical execution. In today's release, I'd like to present a new approach. It's using the trace bait mode analysis. What you would have to do is, in addition to your program flow trace, where you just trace and record what instructions have been executed and how long they took, you additionally need at least here the memory cell for the main task clock. If your trace provides that information, that data trace for this memory cell here, you can go to the analyzer, and I did that in a different project here, and provide a following ICE specification. You provide an attribute specification of the kind I would like to distinguish a running mode, where the memory cell with the symbol main task clock modulo 2 equals 1. In that case, I would like to only accept those snippets where this attribute or this property is fulfilled. Okay, and if we now run the analysis under this additional assumption to ask the trace parser observing that special memory cell, and if it can find this data in the trace, then you will see what happens. So the trace parsing takes some time. Now it's finished, and if I open the graph, let me show it to you. You see the time has decreased, and only a few of the call edges are now red, so means lying on the worst case. And if you have a look into the control flow graph, you can now see that, well, we have in total 29 snippets, and so for this case here, and we select the then branch of this first conditional branch, and then the next one is no longer be covered. You see that it's surrounded by these red borders. That means we only consider trace snippets now where this property is no longer fulfilled. But again, in 6 of these 29 trace snippets, we also enter that branch here, because then the main task clock was also modulo 10 was equal 10 was equal 5, right? So you see that only this feasible combination will now be selected as the worst case, considering this new attribute. The second new feature can be found in the statistics. If we open that one, we now see all, in addition to the standard trace coverage, which was context insensitive, we also have a new trace coverage view that is context specific. So if I click here, you now see here some subcategories. For instance, if we open the memcopy, we see two different contexts, and we would distinguish here the coverage information for these two contexts. In this case, of course, it's kind of boring, since it was a benchmark program and it was asked to be run everything here. So you have a full coverage when you enter a function. So, but in principle, we would distinguish here the different calling contexts and calculate a separate or individual coverage for each context. The last section in today's release video is about new or extended IS2 specifications, and I've selected two candidates here to present. The first one is an extension of the dwarf view to generate a new copy ice area contains annotation that refers to a certain type of functions. And I'd like to show you how this is actually working. So I performed here in our favorite scenarios exercise the 1 millisecond task stack analysis, and I got an unresolved computed call warning. So basically an unresolved function pointer call in the OS error hook routine. And as you know, if we double click on it, we now have this new context menu. I can have a look into the graph basically, and I see that here is some registered error handler variable. It's a global one, is called, but obviously the analyzer does not know anything about which error handler has been registered here. In previous release videos, we showed several strategies how to solve this problem. There are a lot of different ways to get this computed calls resolved. If we have a look to the source code, remember that this register variable is set here, is initialized here in a separate initializer functions, and here it is set to the user error handler. So the easiest way how to resolve this computed call is basically to say it calls the user error handler here, if this is the only location where the registration happens. What you could also do alternatively, remember that, is to analyze this init task function separately with the ValueAnalyzer, right? If you have a ValueAnalyzer add-on, and then collect the initialization for the register error handler and provide or enable a dependency from that initialization analysis to our stack analysis, and then it will also be automatically resolved. These are just two examples, and today I'd like to show you a completely new way how to resolve it, because you could now that you have found out that the register error handler is set here to the user error handler, you could also say, let me have a look to the dwarf view, and well, we just search for the register error handler. Here it is, a global variable, and since we know the type, we also know where what are the functions types this pointer is pointing to. So it's basically pointing to these functions here. What you could do is now, if this is a unique type for unique functions that are exclusively taken for the error handling register here, you could say copy ice area contains data annotation to clipboard. This is a new context entry here. If you do that, we will see that the analyzer now copies a new annotation of the following kind. It says, okay, I'd like to fill the registered error handler with a list of addresses that belong to functions of the very same type. So this is very generic, of course, in this case, but usually people are defining type definitions, type defs, for individual callback functions. And then you could also use the type definition here. I think the analyzer also, if there is a type definition, produces here a second entry in a comment with the type def variant as well. Okay, and if you now run that, it will apply all functions as targets for this registered error handler that adhere this type, of course. And in our case, it's luckily only one function, namely the user error handler, and it will be resolved automatically here. For the last point on today's agenda, I'm coming back to my presentation, and here it's about the if annotation scope that we extended. You remember that you can formulate such an meta or if annotation scope, as we call it. So you can apply certain list of annotations and yeah, depending on some property, some condition. In this case, I'm checking if the analysis type for the analysis I'm going to start equals a stack analysis. Then only then, in this case, I'd like to provide a mapping for my call string length of 2. For all other analysis, the default would be applied. Now we can extend this if annotation scope also by else if and else annotation scopes. So for instance, you could say else if my analysis type is a value analysis, then I would like to increase the call string to 4, so as a kind of medium complexity, and only for all the rest analysis, aiT, estimate, TimeWeaver analysis. Here I would like to spend the most precision, or the highest precision in terms of the call string length. Yeah? So we now have the if, an else if, and an else annotation scope available in aiT. This concludes my presentation of the latest features and improvements for the April release of the binary level analyzers. As usual, this was just a selected subset of all changes and improvements. If you would like to have a complete overview, please have a look to our website here. Thank you very much for your interest. Stay healthy, take care, and bye-bye.